The story of Earth's surface is one of constant motion, a slow yet relentless shifting and reshaping that has been going on for billions of years. Beneath the landscapes we see today, mountains, oceans, valleys, and plains, lies a dynamic process driven by forces deep within our planet. This process, known as plate tectonics, is the mechanism behind the movement of continents, the creation of mountains, the formation of ocean basins, and the occurrence of earthquakes and volcanic activity. To truly appreciate the planet we live on, we must delve into the history and science of tectonic plates and continental drift, which together tell the tale of how the Earth's surface has evolved over eons. At the heart of this story are tectonic plates, the enormous, rigid slabs of rock that make up the Earth's lithosphere, the outermost shell of the planet. These plates vary in size and thickness, some spanning thousands of kilometers across, while others are much smaller. They float atop the semi-fluid asthenosphere, a layer of molten rock that lies just below the lithosphere. The movement of these plates is slow, usually only a few centimeters per year, about the speed at which your fingernails grow. Yet, over millions of years, these movements add up to dramatic changes in the planet's surface. The concept of tectonic plates and their movement was not always accepted. For much of history, people believed that the Earth's surface was static and unchanging. It wasn't until the early 20th century that the idea of continental drift, an earlier theory that laid the groundwork for plate tectonics, began to take hold. The German meteorologist and geophysicist Alfred Wegener is credited with proposing the theory of continental drift in 1912. Wegener suggested that the continents were once joined together in a single supercontinent, which he called Pangaea, and that they had slowly drifted apart over time to their present positions. Wegener's theory was based on several lines of evidence. He noticed that the coastlines of South America and Africa seemed to fit together like pieces of a jigsaw puzzle, suggesting that they were once connected. He also found that similar fossils and rock formations were present on continents that are now separated by vast oceans, further supporting the idea that these landmasses were once united. Additionally, Wegener pointed to evidence of past climates that didn't match the current locations of the continents. For example, he noted that there were signs of glaciation in regions that are now tropical, implying that these areas had once been located closer to the poles. Despite the compelling evidence, Wegener's theory of continental drift was met with skepticism by many scientists of his time. The main reason for this was the lack of a convincing mechanism to explain how the continents could move. Wegener proposed that the continents plowed through the oceanic crust like icebreakers through ice, but this idea was not supported by geological evidence. As a result, the theory of continental drift remained controversial for several decades. It wasn't until the mid-20th century, with the advent of new technology and scientific discoveries, that the idea of moving continents began to gain widespread acceptance. One of the key developments was the discovery of the mid-ocean ridges, a continuous chain of underwater mountains that encircled the Earth like the seams on a baseball. In the 1950s and 1960s, scientists began to map the ocean floor in detail and found that the mid-ocean ridges were sites of volcanic activity and seafloor spreading. Seafloor spreading provided the missing piece of the puzzle that Wegener had been searching for, a mechanism to explain how the continents could move. As new magma rises from the mantle at the mid-ocean ridges, it cools and solidifies to form new oceanic crust. This new crust then spreads outwards, pushing the older crust away from the ridge and causing the ocean floor to move. This process of seafloor spreading drives the movement of tectonic plates and, in turn, the continents that rest upon them. With the discovery of seafloor spreading, the theory of plate tectonics began to take shape. Scientists realized that the Earth's lithosphere is broken into several large and small tectonic plates that move relative to one another. These plates can interact in several ways. They can collide, pull apart, or slide past each other. The boundaries where these interactions occur are the sites of significant geological activity, including earthquakes, volcanic eruptions, and the formation of mountains.
One of the most dramatic examples of tectonic plate interaction is the formation of mountains.
When two continental plates collide, neither plate is dense enough to be subducted into the mantle. Instead, the collision causes the land to buckle and fold, pushing the crust upwards to form mountain ranges. The Himalayas, for example, were formed by the collision of the Indian plate and the Eurasian plate. This process is still ongoing today, as the Indian plate continues to push northwards into the Eurasian plate, causing the Himalayas to rise at a rate of a few millimeters per year. In contrast, when an oceanic plate collides with a continental plate, the denser oceanic plate is forced downwards into the mantle in a process known as subduction. As the oceanic plate sinks, it melts and forms magma, which can rise to the surface and create volcanic activity.
This process is responsible for the formation of volcanic mountain ranges, such as the Andes in South America and the Cascade Range in North America.
The Pacific Ring of Fire, a horseshoe-shaped zone of high volcanic and earthquake activity, is another example of the effects of subduction zones around the edges of the Pacific Ocean. Tectonic plate movements also play a crucial role in the formation and destruction of ocean basins. When tectonic plates pull apart at divergent boundaries, magma rises from the mantle to fill the gap, creating new oceanic crust. Over time, this process can lead to the formation of a new ocean basin, as happened with the Atlantic Ocean. The Atlantic began to form about 200 million years ago when the supercontinent Pangaea began to break apart, and the continents of Africa and South America started to drift away from each other. As they moved apart, the gap between them filled with magma, forming the Mid-Atlantic Ridge and the Atlantic Ocean Basin. The movement of tectonic plates is also responsible for the opening and closing of oceans over geological timescales. The concept of the Wilson cycle, named after Canadian geophysicist J. Tuzo Wilson, describes the cyclical opening and closing of ocean basins. According to this concept, the Earth's surface is constantly being reshaped as continents collide, merge, and break apart. Over hundreds of millions of years, supercontinents form and then fragment, leading to the opening of new oceans and the closing of old ones. One of the most significant consequences of tectonic plate movements is the occurrence of earthquakes. Earthquakes are caused by the sudden release of energy along faults, which are fractures in the Earth's crust where tectonic plates are moving relative to one another. Most earthquakes occur along plate boundaries, where the plates are either colliding, pulling apart, or sliding past each other. The San Andreas Fault in California is a famous example of a transformed fault, where the Pacific Plate is sliding past the North American Plate. The friction between the plates causes stress to build up over time, and when this stress is released, it results in an earthquake. Volcanic activity is another direct result of tectonic plate movements. As plates move apart at divergent boundaries or as oceanic plates are subducted at convergent boundaries, magma from the mantle can rise to the surface, leading to volcanic eruptions. Some of the most powerful and destructive volcanic eruptions in history have been linked to tectonic plate movements, such as the eruption of Mount Vesuvius in AD 79, which buried the Roman cities of Pompeii and Herculaneum, and the eruption of Mount St. Helens in 1980, which was one of the most significant volcanic events in the United States in the 20th century. The movement of tectonic plates is also responsible for the distribution of natural resources. For example, the formation of oil and gas reservoirs is closely linked to the movement of plates and the creation of sedimentary basins. These basins form in areas where the Earth's crust has been stretched and thinned, creating space for sediments to accumulate over millions of years. As organic material is buried and subjected to heat and pressure, it transforms into oil and gas, which can then be trapped in porous rock formations. The distribution of minerals is also influenced by tectonic processes. Many valuable minerals, such as gold, copper, and diamonds, are found in areas where tectonic plates have interacted in ways that concentrated these resources. For example, gold deposits are often found in regions where ancient tectonic activity caused the formation of mountain ranges, which created the right conditions for gold to be deposited in quartz veins. Understanding tectonic plates and continental drift has also provided insights into the history of life on Earth. The movement of continents over geological time has had a profound impact on the evolution and distribution of species. As continents drifted apart, populations of plants and animals that were once connected became isolated from each other, leading to the development of unique species on different continents. This process, known as vicariance, has played a key role in shaping the diversity of life on Earth. The study of plate tectonics has also shed light on the mass extinctions that have punctuated the history of life on Earth. For example, the Permian-Triassic extinction event, which occurred about 252 million years ago and wiped out approximately 90% of all marine species, is believed to have been linked to massive volcanic activity associated with the formation of the supercontinent Pangaea. The breakup of Pangaea and the subsequent opening of the Atlantic Ocean may have also played a role in the extinction event by altering ocean circulation patterns and triggering climate changes. As we continue to study tectonic plates and continental drift, we gain a deeper understanding of the forces that have shaped our planet and the processes that continue to influence its surface. The theory of plate tectonics has revolutionized the field of geology and provided a unifying framework for understanding a wide range of geological phenomena. It has also highlighted the dynamic nature of our planet, reminding us that the Earth is not a static, unchanging body, but a living, breathing entity that is constantly evolving. Today, scientists use a variety of tools and techniques to study tectonic plate movements and their effects on the Earth's surface. Satellite technology allows us to measure the movement of plates with incredible precision, while seismic instruments help us monitor earthquakes and volcanic activity. Computer models are also used to simulate the movement of plates and predict future geological events. The study of tectonic plates and continental drift is not just about understanding the past, it is also about preparing for the future. By studying the movements of plates and the history of geological activity, we can better predict and mitigate the impacts of natural disasters such as earthquakes and volcanic eruptions. This knowledge is crucial for the safety and well-being of people living in tectonically active regions around the world. In conclusion, the story of tectonic plates and continental drift is one of the most fascinating and important chapters in the history of Earth science. It is a story of discovery, of challenging old ideas and embracing new ones, and of uncovering the forces that have shaped our planet for billions of years. It is a story that continues to unfold as we learn more about the complex and dynamic processes that govern the Earth's surface. And it is a story that reminds us of the incredible power and beauty of the natural world, and our place within it.